this lecture, we will discuss some of the basic mechanisms in which nodes in a distributed system communicate. So these are very large distributed systems. So in such distributed systems, often a node only knows the IDs of some of the nearby nodes, right? It doesn't clearly know which nodes comprise the entire network. So this is not known. So the communication between nodes in such cases is tricky because given the fact that we don't know all the nodes in the network, we will not know if the message is reaching or not. So what we will discuss in this lecture set, in this lecture actually in this video, are basically two kinds of protocols, epidemic protocols and gossip based protocols. So epidemic protocols are clearly more popular in the literature, such as anti-entropy and rumor mongering. In comparison, gossip based protocols are not that popular, but nevertheless they are also used, and we will see that they are heavily used in a lot of the distributed systems, particularly in modern systems where it can be where we are talking of large web scale systems. So these distributed systems are kind of distributed all over the internet. So the key idea of a distributed system is to form an overlay network. An overlay network is basically a virtual network, essentially a network over a network. So regardless of how the physical organization of the network is, so they could be wireless links, they could be Ethernet links, there are a wide variety of possibilities. Alright. So regardless of that, we create a virtual network, and that is known as the overlay, where as you can see this is a ring shaped overlay, where each node just knows the ID of its left neighbor and the ID of its right neighbor. Alright. Essentially it's clockwise neighbor and its anti-clockwise neighbor. And we shall see that such overlays form the foundation of many of today's peer-to-peer networks, and most of our enterprise networks use such kind of overlays, and most of the common ones are clearly a ring and a star. So this is more like a structured network. So the definition of a star is something that all of you know, but nevertheless might not be a bad idea to define, where we have one central node that can be like a server or some sort of a base server, and then we have many other client nodes connected to it. So a typical client server computing, where we have multiple clients on a single server, would use such kind of a star shaped overlay. So why do I call it an overlay? Because this is not the real organization of the network, it is a virtual organization. Alright. So given that it's a virtual organization of the network, I'm using the term overlay. A ring in comparison is way more popular. A ring is the basis of a structure called a distributed hash table or a DHT, and they started coming in a big way in third generation peer-to-peer networks. So here what we do is that we can have a large system over the internet, but that's okay. Regardless of where they are, we just connect them as a virtual circle, right, as a virtual ring. So star shaped overlays and ring shaped overlays form the basis of what we call structured networks. But our entire discussion here has centered around unstructured overlay networks, where there is no fixed global topology, right? So a fixed global topology is definitely not there. A node typically knows a subset of other nodes, and a node is pretty much blind. So somebody can argue that in a ring shaped overlay also a node is pretty much blind, in the sense this node only knows about its clockwise successor and anti-clockwise successor. But at least there is a structure. In an unstructured overlay network, there is no structure, right? And so there is no global structure, you only have a small local structure, and that too, if there is one, sometimes you just know the list of a few nodes, that's it. So when we are talking of such unstructured networks, there is a problem. If I want to send a message or multicast a message to a group of nodes, there clearly is a problem, and the problem is that I may not be able to reach the entire network because I will not be aware. I will not be aware of the state of the entire network, right? And since I'm not aware of the state, that will to a large extent cause a problem. So this is not there with structured networks with a ring or a star, but we are mainly looking at unstructured networks here, and there is an issue. So what I can do is that I can send a message to all the neighbors. Right? I can ask the neighbors to forward messages to their neighbors and so on. So this will kind of exponentially flood the network. But the negative aspect of this is this will create an exponential number of messages which will become almost impossible to handle, and there is no guarantee that the entire network of nodes will actually be reached. So we need some way of kind of roping this in. A pure exponential way is a bad way. And furthermore, we need some mathematical techniques for analysis. For analyzing this system, for analyzing this setup, we need some mathematical techniques. So what I will discuss at the beginning is this paper, Epidemic Algorithms for Replicated Database Maintenance, by, as you can see, a long list of authors, published in PodC 1987. So what was the basic problem that was being solved? The basic problems was that there used to be a big company called Xerox. So we don't get to hear Xerox a lot in 2020, but Xerox at one point was a preeminent power in computing technology. So for example, the graphical windows that you see, large part of that came from Xerox, the mouse came from Xerox. So Xerox Spark Research Lab used to be counted as maybe the world's best research lab in this area. And I mean, there was a competition with Xerox and IBM. So Xerox had a large corporate intranet which did not have a structure, it was unstructured, and they were maintaining databases. Alright. So these databases that were being maintained, they needed to be kept in sync, which meant that updates had to be propagated. And how to propagate updates, given that there were so many machines, and those days network communication was expensive in terms of time at least. This was a problem. So updates are injected typically at one site and they have to be propagated to the rest of the sites. And given that one site did not have a global list, this became a problem. So there are three main approaches that we should look at. The three main approaches are direct mail, where an update is sent from one site to all sites. The reason that direct mail could not be used was basically because number one, there were too many sites and their exact list was not known. And furthermore, this is a sequential process, it's not a parallel process, so it will take a lot of time to send messages, and we are dealing with a slow intranet situation over here. So that's the reason the two broad approaches that were used are anti-entropy and rumor mongering, and these approaches later on were worked on by a generation of researchers, and today there are very sophisticated anti-entropy and rumor mongering methods which are actually used by many of the companies that affect our lives, such as Amazon, Facebook, LinkedIn, and so on. Of course, not the same way that Xerox used, but in a modified version that is suitable to those companies, right? Suitable to the systems of those companies and improved. So anti-entropy says that we choose a site at random and we synchronize the contents of the database by exchanging contents, which means that I randomly choose a site, I give it my updates and I take the updates of that site and update my own database, right? So both of us know whatever we knew earlier, in the sense that, let's say, whatever is new the other side knows, and whatever the other side knows that I don't know, that is transferred to me. So our knowledge levels become equal. This is anti-entropy. So anti-entropy by definition does not stop, because we keep on finding sites at random and we keep on exchanging information with them. The other approach is rumor mongering, where a site distributes updates to other sites. When a site sees that most of its neighbors have the update, it ceases to uh, transmit updates with that frequency, it reduces its frequency of transmitting updates. So we say that this is like spreading a rumor. So the rumor in this case is the update. So the rumor ceases to be hot and gradually it dies away, right? It fades away. So we will do a little bit of a mathematical analysis over here. So we will create three kinds of sites: infective, susceptible, and removed. An infective site is something that has already received the update and willing to propagate. So incidentally, these terms have been taken from the literature of epidemiology, which sees how epidemics propagate. And given that I'm recording this video in the middle of the coronavirus pandemic, these terms will appear to be extremely relevant, right? So an infective is essentially a person, in this case a site, that is willing to propagate. Susceptible is somebody who is not a site, basically, that has not received the update, so it can be infected later. And removed is that you are not participating in propagating updates. So in a sense, you have disconnected yourself from the network as far as updates are concerned, right? So that's the term. So anti-entropy, it takes longer to propagate updates as compared to direct mail. That is true. It does not have a built-in termination mechanism, but it is what is called a simple epidemic, in the sense that it is easy to propagate information, right? And that too, very easily it is possible to propagate, and it's nice and simple. So it's a simple epidemic. In comparison, rumor mongering is a complex epidemic because it has a built-in termination mechanism. But unlike anti-entropy, there is a problem. So anti-entropy guarantees that, look, ultimately all the sites will have received the update. But in rumor mongering, there is a chance that updates might not reach a node, which basically means that there is a chance, there is a possibility, a probability that the updates might not reach a certain node. A node in this case is a site. So let us start with anti-entropy. So let us say that a network contains S sites and the database copy K at a given site small s. Its value is essentially a tuple. The tuple K has two parts to it. The first is the actual value of the update and the T is the timestamp. So basically any newer update will have a higher timestamp. So this is how we differentiate between old updates and new updates. It was necessary to add this timestamp in the network because it is possible that messages that circulate older updates might still be alive in the network, and this is how we will distinguish between old updates and new updates. And clearly old updates should be discarded and the new updates are the ones that should be applied. And this will be decided on the basis of the timestamp. So, in the anti-entropy algorithm per se is easy. So, we have two kinds of anti-entropy, push and pull. So, if there are two sites S and S dash, what push does is it pushes the updates of S to S dash. So, it basically sees that if S has a higher timestamp, then it sets S dash's value to S. The difference between push and a pull is that in a pull, S dash essentially sends a pull message and it asks S for the most recent copy of data that it has, right? So, the pull basically again does the same thing, that if S has a lower timestamp than S dash, all right, then SS value is set equal to S dash's value. So, it is important to look at this once again. So, in push what we are doing is S is pushing to S dash. In pull what we are doing is that S is essentially asking S dash, look, do you have any data, right, that might be of potential use to me. So, if S has a lower timestamp, then what it will do is it will kind of pull the data from S dash, right. So, S will set the value of its data to S dash's value. Of course, if S dash's data has a more recent timestamp. So, let us temporarily erase this figure and look at, oh sorry, I can use the eraser over here. So, I realize that something that I described earlier might not be 100% correct. So, let me take one more attempt at explaining this. So, pull, what happens is that we have two sites S and S dash. So, S sends it a pull message saying, do you have any updates for me? And if it does, then S dash sends an update. S compares the timestamp. If it has a smaller timestamp, well then it takes up S dash's update. All right. So what is the semantics of push and pull? Well, in push, S is pushing its updates to S dash, and in pull, S is asking S dash, look, do you have a new update? And if S dash has a new update, it sends it to S, and clearly, if from S's point of view, if it is new, S applies it. A push pull is a combination of both the schemes, both push as well as pull, and so that's the reason I am not describing it separately. So, let us now do a little bit of math and understand what exactly is going on here. So, what we are out to prove is that anti-entropy distributes updates in order of log n time. This is a result from epidemic theory. Try to apply this to a coronavirus scenario. In this case, n is the total number of nodes. So, in a pull based algorithm, let Pi be the probability of a site remaining susceptible after the ith cycle, right. So, for a given site, let us say after the ith cycle, the probability it is still susceptible is Pi. What is the probability that it is susceptible even after the I plus 1th cycle? Well, what would happen? We are dividing this into rounds, and in every round, the ith node over here will contact some other node, because it is a pull based system, and if the other node has a recent update, it will get it. If that is the idea, then let us see. So, this is essentially the conditional probability over here is that what is the probability of the other site to actually contain an update, alright, or rather not contain an update. So, if it does not contain an update, and since we do not remove nodes in anti-entropy, it will still be susceptible. So, so how do I write the probability? Well, the probability, let us say that the event that I am susceptible. Let's say that event is x, that is equal to I plus 1, which means in the ith cycle I am susceptible, is the probability that I am susceptible in the ith cycle multiplied with the probability that, let's say, I contact a node which is, given that I was susceptible in the ith cycle, I contact a node, let that be event y, and that node is susceptible, right? That node is not infected. So then the first probability is clearly pi, and the second is that I contact a subset of nodes which are not infected. So the subset of nodes that are not infected, that is again equal to pi. So the net probability is pi into pi. So what am I trying to say? I am trying to say that, look, this quantity is pi by definition. This quantity, the fact that I contact some other node and that turns out to be susceptible, again arises from the definition of probability. That's the way probability is defined, that it is the size of the interested points divided by the size of the sample space. So in this case, the number of interested points, which are the ones that are not infected, still susceptible, divided by the sample space is pi. So that is where the second pi comes from. If I multiply them, I get pi square. So if you are not able to understand this explanation, I would suggest that hold on, let me just try to see if I can clean off parts of the page. Yeah, so as I mentioned, if you are not able to understand what I just said, I would suggest, and that too rather strongly, that you look at texts in probability, and that will kind of clear up most of your doubts. All right. So that will clear up, and that will tell you why we were able to get pi square over here, which is just a product of two things. The fact that it's susceptible in ith cycle multiplied by the probability that if it is susceptible in ith cycle, what is the probability that it will be susceptible in I plus 1th cycle. Both are equal to pi, so that's where we get pi square. So this will happen in a pull based algorithm, not in a push based. So in a push based algorithm, again this comes from the law of large numbers. So this is the right time to go to Wikipedia and study the law of large numbers. So the expected number of infective nodes, the nodes that are not susceptible, is n times 1 minus pi. That should be easy, because the probability a node is infective is 1 minus pi, and the total expected number is n times this. This follows from the law of large numbers, the weak law in particular. The probability that I do not contact a node is 1 minus 1 by n. So what is the probability that a given node is susceptible in the I plus 1th cycle? Well, again, it is the probability that the node is susceptible in the ith cycle, right? Right. So it's the probability that this node is susceptible in the ith cycle multiplied with the probability that no other node contacts it in the ith round, which is infective. So no infective node contacts it in the ith round. That is important. So how many such nodes are there? Well, so the point is that there are n times 1 minus pi such nodes. None of these nodes contacted me. So for each node, the probability of not contacting me is 1 minus 1 by n. This raised to the power n times 1 minus pi, which is essentially this quantity, is the probability that I remained susceptible in the ith round, given the fact that at the beginning of the ith round I was susceptible. So, we will use a well known result in calculus, which is 1 minus 1 by x to the power x as x tends to infinity is equal to 1 by e or e raised to the power minus 1. So, this again is a result from calculus that we shall use, and this will tell us that pi plus 1 is equal to pi, well pi comes from there, alright, 1 minus n to the power n. So, of course, here an assumption that I am making here is that pi is rather small, right. So, this assumption is the probability that a node is still susceptible. Let us say that this probability is kind of small. So, we can approximate this to e raised to the power minus 1, which is pi by e. Alright. So, if I go with this small, so it is even written that is for large n and small pi, I can approximately have this assumption that the probability of susceptibility every round falls by a factor of 1 by e. 1 by e you would have encountered in many other scenarios. It is around 0.37, right. So roughly let us say that every round the probability of susceptibility falls down by 37%. So, after a few rounds itself it will become small, very small, and then it will continue to decrease. But mind you, this assumption is only valid for small pi. So, let me now again erase the ink on this slide and let us look at alright. So, let us look at these two expressions. So, if pi is small enough, then basically this expression reduces as a square, because given that these are probabilities, these are actually fractions. So, this essentially gets squared and then to the power 4 times, 8 times, and so on and so forth. Whereas, this reduces by a constant factor, alright. So, a pull will reduce the probability of susceptibility, which should ideally become 0 at the end. So, this should tend to 0 as a square, and this is by a constant. So, we need to now understand which one is better. So, the point is that it all depends on whether it is the beginning or whether it is the end. So, let us say this is a big network. At the beginning, let us say if we use a pull based method, then nobody is going to get anything. The reason that nobody is going to get anything is because there are very few susceptible sites. So, there will be no advantage because nobody is really going to contact the few sites that are still infected. So, at the beginning, push based methods are clearly better because at least they are reducing it by a constant factor. Of course, we have assumed small pi, but even if let us say you were to do a simulation, you will still see it reducing quite significantly, quite quickly as compared to pull based methods. So, at the beginning definitely a push based method is preferred, and what the push based method actually does is that it propagates the updates to as many nodes as it can, as many as it can, gradually as the updates have disseminated, right. There will still be a small minority of nodes that have not gotten the update. Well, then they can revert to a pull based method where they will contact nodes that have reached, that have gotten the update, that are infected, and then they can fetch the update from there. That is why we say that pull based methods are better at the end. So what was the thing? From maths we can say that look, at the beginning push based is better because you are just coming into the network with an update. So contact as many people and spread the update. However, towards the end, pull based methods are better, because even if, let's say, I were to do push, I will still not be able to contact the ones with high probability, of course, that have not received the update. But in pull based methods, the nodes that have not received the update will continue fetching them, and as they get into a minority, the probability of they actually hitting a node that has the update kind of increases, right? So that's why any method has push at the beginning, pull at the end. So this is anti-entropy for you, can be optimized. Instead of comparing the entire database contents, well, compare the timestamps of the recent entries. If the timestamps match, well, nothing much needs to be done, because that will tell you that earlier entries are there. And if they do not match, well, then update the recent entries and compare what are called checksums. So checksums are essentially think of them as advanced versions of parity bits, where, let's say, if we have a 64-bit checksum, it kind of uniquely identifies the contents of the entire database. So the entire contents of the entire database is kind of compressed to a 64-bit number, and that uniquely identifies it. It's like a hash, right? It's a hash. If the checksums do not match, which means the hashes do not match, means that there will be one small little difference somewhere. So there is a need to transfer the entire databases and sync it. Otherwise, per se, there is no need. Okay. We can compare hashes for older entries, and for recent entries, very recent entries, there we can compare the entries themselves. So we have looked at anti-entropy, we have looked at the push based mechanism. We have looked at the pull based mechanism. We have said that, look, this is better at the beginning and pull is better at the end. Now we look at rumor mongering, which is the second kind of epidemic protocol. So why epidemic protocol? Because these protocols have come out of epidemic theory, something that you see in excess in these COVID pandemic days. So here also we'll have the same idea of susceptible, infective and removed. In this case, it's not the number of nodes, but rather the fraction. So that is why we have S plus I plus R is equal to 1, right? So these are just the fractions. So recall that this removed category was not there in anti-entropy, but the removed category is there in rumor mongering. All right, S plus I plus R is equal to 1. So we'll use some calculus here to derive the results. So let us look at the rate of decrease of susceptible nodes, right? So this is ds by dt. So ds by dt will have a negative sign, because, well, ds by dt is pretty much the rate of increase, but the negative sign makes it the rate of decrease. So this is clearly proportional to two quantities. It is proportional to the fraction of susceptible nodes, because clearly if there are more susceptible nodes, then more nodes will get contacted, more nodes will get infected, and more nodes will enter the infective category. It is also proportional to the number of infective nodes, because more are the number of infective nodes, right? Higher is the proportion of the number of infective nodes. Proportionately higher is the rate of decrease of susceptible nodes. So, well, these equations do hold, let's say, for a steady state range, where, of course, where, let's say, the number of infective nodes is not much, it's clearly not saturating, Similarly, the number of saturating nodes, the number of susceptible nodes is also not extremely large, where this may not hold, or it's not extremely small. So there are clearly ranges where this equation holds exactly and ranges where this equation doesn't hold all that well. But let us say that these are all empirical laws, in the sense they have been observed to hold at least most of the time, and they also can be derived from the simple informal explanation that I gave, right? That the rate of decrease of the susceptible nodes is, in a sense, proportional to both the quantities, and both the quantities are thus, we consider, a product of these quantities. Furthermore, let nodes lose interest in propagating rumors by a probabilistic factor of 1 by k, which means that nodes will gradually lose interest in propagating the infection. In this case, it is a rumor with the rate 1 by k. So this equation is derived like this, that di by dt, which is again the rate of increase of infective nodes. Well, this, for reasons similar to the previous reason, is also proportional to Si, which means proportional to the product of the fraction of both susceptible as well as infective nodes. And the reason is similar to the reason that we gave over here. However, there is a damping factor, right? So let us understand this damping factor. So this damping factor is clearly proportional to the number of infective nodes, which should be the case, because uh, higher is the number of infective nodes, higher should be the damping, right? It is also proportional to the number of nodes that are not susceptible. So if we go back to this equation over here, then the nodes that are not susceptible are either infective or removed. Alright. So basically it is proportional to 1 minus s. So 1 minus s is basically the non-susceptible part of the network, and as that increases, that does put in a damping effect, and here is the factor 1 by k that we talked about, and the factor k does determine how quickly the rumor dies or how quickly the rumor fades away. Alright. So as I have said, the equations have been derived by a combination of two things. The first is empirical observations, and they do tend to hold for a large range of I and S, right? They do, this approximate relationship does hold, and also from the informal arguments that I just provided up till now, right? Well, informal is a bad word, let me call it the semi-formal arguments that have been provided to you, right? So they basically look at the interaction of these two factors, all right, and so the interaction of these two factors pretty much determines how the rumor is going to propagate. See, if I were to solve both of these equations, which would be this equation over here and this equation over here, if I were to solve them, then I can always find the rate of infective nodes, the fraction of infective nodes, as a proportion of S, right, as a function of S. So this turns out that it is a sum of a linear function and a log function, with the damping factor playing a very key role, as you can see over here. So what are we getting to see over here? What we are getting to see is that t we have eliminated, and we basically have I as a function of S, and of course we can see the damping factors play a key role. So this the derivation of this is clearly given in the paper, and you can take a look at it. This is just a brief summary of what I am showing, and given that we are in the middle of a pandemic now, I would invite all of you to take some maybe coronavirus data and try to fit it with whatever you think is the damping factor. So the damping factor can be derived from what they are quoting as the R number, which is the number of people that one person infects during his or her coronavirus affliction. So the damping factor can be derived from there. So for different damping factors, you can fit these curves and see how the infection will evolve over time. So if I were to plot it as a fraction of S, see initially of course all the nodes are susceptible, so we will start from here and we will walk backwards this way. So if we see k is equal to 1, so if k is equal to 1, what we get to see is that we see a curve like this. So basically the multiplicative damping factor is actually 1 by k. So 1 by k in this case is 1. So what we are seeing is that the rate of infective nodes will increase and then abruptly fall to 0. Well, not abruptly, but let's say in this range it will fall to 0. So ultimately we will have, when the number of infective nodes is 0, which means no more infections can actually happen, right? No more nodes will actually get the updates. We will see that around 20% of the nodes are effectively left out, right? So they are still susceptible or they are left out. So this clearly depends on the damping factors. If I were to make k as 1.5, which will make that effective product term 1 by 1.5, so we see a shift of this curve. We see a shift of this curve towards the left, and gradually as the damping factor k, well, I should actually call the damping factor as 1 by k. So gradually as that reduces or as k increases, we will reach this point, and the moment that the curve actually reaches this point, it will basically tell us that look, at this point no node will be left uninfected, in the sense all the susceptible nodes will become infected, right? So there will be no node that is not susceptible, which means that it is infected. And of course I show the figure curve here for k is equal to 2, and k equal to 2, which means 1 by k will become 0.5. That is clearly too much, in the sense we can see that all the nodes at the end will remain infective, alright, and the number of susceptible nodes will actually fall down to 0, alright. So this is the key point over here, okay, that at the end over here all the nodes still remain infective and no node is susceptible, and it's clearly not removed from the network. Alright, so now let us see what percentage of nodes are still susceptible when no other node is infected, that is 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 equal to 0. So which is essentially the nice point where we try to kind of estimate this residue over here, which is this much. So this can easily be derived to be this. So we can see that it exponentially decreases with k, and this value is called the residue, and some nodes will still remain susceptible. So let us now look at a few more fundamental relationships. So the residue is the sites that are still susceptible after the end of the epidemic, and the traffic is the average number of messages that we send per site. So let us say we send m updates per site, and there are a total of n sites. So we'll have a total of nm updates. The chances that a site will miss all the updates and still remain susceptible is 1 minus 1 by n. So we have seen this before. This is the probability that any other site misses this, multiplied with itself nm times, which is 1 minus 1 by n to the power nm. which is e raised to the power minus m. So what we can see is as the traffic increases, in the sense number of updates per site, as that increases, the residue decreases and ultimately the residue tends to 0, right. So if we just increase the traffic, then the residue will reduce and ultimately it will come down to 0. And how will it come down? Well, it will come down using this exponential relationship over here. So then what is the key learning that we got from here? That rumor mongering can miss sites. It clearly can, because there is a residue. After a certain time, we can run the anti-entropy protocol. So what we can do is we can do rumor mongering for some time, and the rumor mongering is nice, good, it is self-terminating. But after a certain time, we can again run a background kind of a slow anti-entropy protocol to ensure that all the nodes are genuinely covered. And let's say whenever they discover a missing update, we can also add a threshold to this. They can then start a hot rumor in their local region such that we can quickly cover their local region and the rumor itself will die or fade out over time. So Xerox Clearinghouse did use many of these mechanisms. In addition, it did some amount of redistribution via direct mail also. This is something that we have not discussed. So what we have discussed is primarily anti-entropy. There we said look at the beginning you follow a push based technique. Then towards the end you follow the pull based technique. Then we discussed rumor mongering. So we talked about the residue. Alright. And we also said that look, the residue is kind of e raised to power minus m. So basically increase the traffic per site and the residue will quickly fall down to 0. So the details are given in the paper of how exactly the residue and removed nodes etc. are calculated. But this should be enough to at least give you a feel of what are the broad mechanisms of these epidemic protocols. So these are modeled on the lines of an epidemic. So that's the reason they are called epidemic inspired protocols. So now let us look at other finer aspects, deleting nodes and spatial distribution. So we can also treat the deletion of any item as an update, the same way that when we modify an item we call it an update. We can also treat the deletion as an update and issue a death certificate for a node. The death certificates themselves can be propagated via rumors or anti-entropy. And of course, when a death certificate meets a later update for that item, it basically means that that item, whichever site updated the item, did not get the death certificate. So then of course the update gets cancelled. But of course we need to discard death certificates. Well, if we are using rumor mongering, they will ultimately fade out. Otherwise we define a time threshold. If a death certificate is older than the time it takes to propagate the update to all sites, we can delete it. So essentially some sort of a max threshold, and if let's say the current time minus the time of the death certificate is more than that, we just delete it. At some sites we can still maintain, called retention sites, we can still maintain the death certificates such that later on, let's say long time later there is some update hiding somewhere, then that update can be checked against this death certificate. So the retention sites can do that. Alright, so something similar was also used in the Xerox protocol. So now let's come to the idea of a dormant death certificate. So this is that we keep a death certificate only at a few nodes. If it collides, this should be if it collides with an update, then of course we activate the death certificate and propagate it, which is what we discussed in the previous slide as well with regards to retention sites. So what if a dormant death certificate meets an obsolete update? Well, in this case, we reactivate the dormant death certificate and distribute it. It is possible that a legitimate update can be cancelled if we don't set its time properly. So, of course, setting and managing the time is rather important. So, we can have this can be solved by using version numbers for updates. So, what will happen is that a death certificate can have two timestamps, the original timestamp and an activation timestamp. The original timestamp will be used to cancel updates, right? And the activation timestamp will be used to ultimately get rid of the death certificate, which means that if, let's say, the activated death certificate has been propagating for a long time, we can discard it. So what is the broad idea? Well, the broad idea is that, look, in an unstructured network, our messages can be floating around undetected, right? It's a large network. Some node will have some message. Later on, it will wake up and start propagating the message. So if we delete a node, it might still not lead to an actual deletion, because it is possible that maybe a long time later some node will show up with a message that will update that will update some data that has already been deleted, correct? And so then, I'm sorry, if you delete not a node, but if you delete some data, a later update can always be there lurking around. So that's the reason we had this notion of death certificates stored at retention sites. So they will have an original timestamp, and whenever there is a collision of this dormant death certificate with an update, you just look at the timestamp. If the timestamp is after the data died, well, you cancel the update. But then there is a need to reactivate the dormant death certificate and again recirculate, because it appears that there are several sites that have not gotten the original death certificate. Now the question is, what should be the time on it? Well, don't change the original time, that remains, but also have an additional time called the activation time. So why is this time required? Well, this time is required to see for how long has this version of the death certificate been in circulation. If it has been in circulation for a long time, to reduce the traffic in the network, we can just kill that dormant death certificate and remove the messages. Now a few more issues. So we will discuss some results, of course, without proof. The proof is there in the paper and in the references. Consider the fact that it takes time to send a message depending upon the distance to the destination. Some known results, again presented without proof. If a node can contact only its neighbors, it takes order n time to spread an update using anti-entropy. So that should not come as a surprise. So let's say if this is a ring and let's say there is one site, if I can only contact my neighbors, this is how I go, and it will take order n time. However, if a node can contact any other node, it will take order of log n time to actually transmit the message using anti-entropy. And this again should not come as a surprise, because initially we just do a push based system, and a push based system we reduce something by a constant factor, and let's say if this factor is e, and let's say we have k such rounds. So so in every site we reduce the susceptibility by 1 by e, so we can also approximate that to saying that we increase the number of susceptible sites by e, which again is not totally correct but serves as an approximation kind of. And so then we can say that for e to the power k equal to n, well, this means that the natural log with respect to e of n will be equal to k, right, which is the number of rounds. So that is roughly how the term order of log n comes, but of course we do push at the beginning, pull at the end, doesn't matter. It just takes log n steps. You can kind of keep that in mind without going into the details of a rigorous proof, that this is the time it takes anti-entropy to reach convergence, or roughly all the nodes. We can then kind of extend this with some specific results. So let the probability of connecting to a site at distance d, so let the distance be defined as the number of hops in the network, let the probability of that be d raised to the power minus a. Alright. So this is basically d raised to the power some quantity, whereas a is greater than 2, which is basically it is, and a is greater than 2. So this is kind of stronger than the inverse square law. So it will take a long time to converge, which is n to the order of n to the power k time for convergence. Alright. And this kind of can be seen as a generalization of this result. On the other hand, if a is less than 2, which means it is kind of weaker than an inverse square law, in the sense maybe it's 1 by d or 1 by d to the power 1.5, something like that, then it will take order of polylog time for convergence. Again, a generalization of this result. For convergence, it will take order of log n to the power k. Alright. So the important, I'm just moving to another slide to give myself some space. So the important point over here, mind you, this is just a continuation of the previous slide. The important point is that look, in any epidemic based algorithm, if you want to achieve a polylog time convergence, which means the message reaches everybody, particularly using anti-entropy, then you need to contact random nodes with a probability, right? So this basically means that just contacting neighbors and so on is not good enough. There should be some facility of contacting even far away neighbors with a reasonably decent probability, such that the epidemic can kind of spread faster. Alright. So coronavirus doesn't work that way. In coronavirus, it's still a neighbor to neighbor transmission, of course, depending upon how neighbors are, because so that's the reason it hasn't engulfed the entire world yet. But in an epidemic kind of scenario, if we really want to reach everybody, then a should be less than 2, and if we want to restrict it, a should be greater than 2. Alright. So this is when from a polylog it will become a polynomial. Alright. So we did take some space out of this slide to kind of discuss the results of epidemic based distribution. So now what we will do is first apologize for using the real estate of the gossip algorithm slide, and then discuss gossip based algorithms. So gossip based algorithms are of a different kind, they are of a different nature, they are not based on epidemics. So the key reference that we will use is actually this paper, a gossip style failure detection service. And this is one of the seminal references in this area. So it is that if a set of nodes fail, design a failure detector that detects failure by gossiping. Right. So gossiping is basically that you just pass on that information to whoever you know. So the model of failure is fail stop, which means if a node does not respond to a message for t seconds, we say that it has most likely failed. And the important thing is, similar to rumor mongering and anti-entropy, with n the algorithm needs to scale. So we will look at such gossip based mechanisms next. We will now discuss the gossip protocol. So the aims of the protocol are as follows. The first is that the probability of a false positive, which means that we say that a given node has a failure, but actually it has not failed. This is the probability of a false positive. This is independent of n. So this is a rather strong assumption, or rather a strong aim, in the sense that regardless of the scalability of the network, our probability of a false positive is bounded and it is not dependent on n. Furthermore, our protocol is resilient to message loss and network partitions. So regardless of the fact that networks are partitioned, messages are lost, our protocol can still function. And the scalability in detection time is achieved in the sense the time it takes to detect all failures is order of n log n. And if the clock drift across the nodes is negligible, then the algorithm detects all failures with a known mistake probability. And the increase in bandwidth, which is pretty much the number of messages, is linear in terms of the number of processes. Alright. So, the key operative point here is that the probability of false positive is bounded. The detection time is order n log n, roughly linear, and the bandwidth is linear. So, what we do is that each node maintains a message list, right, a list of messages, and each of the items in the message list contains 3 fields. The fields are member ID, timestamp, and heartbeat counter. So, member ID is clearly some information about another node. So, the ID of that node is being called member ID. So, what we do is that every t gossip seconds, each node will update its heartbeat, increase its heartbeat counter, and send a gossip message to a randomly chosen node. Something similar to anti-entropy is done here. So, the heartbeat is a monotonically increasing counter, and an increased heartbeat tells the rest of the nodes that it is alive. The gossip message contains the member IDs and their heartbeats. So, basically the gossip message can also include the message list, which is the member ID, timestamp, and heartbeats of all the information that a given node has. The receiver will merge the message lists, which basically means that for the same member ID, it will take the larger heartbeat and it will adopt the larger heartbeat counter for that node. Finally, the timestamp for a member indicates the last time that the receiver thinks that a node has updated its heartbeat counter. So, let us say that the heartbeat counter for node number 20, where this message list is a part of node number 10, right, its heartbeat currently is 11. So, the timestamp for this entry essentially indicates the last time that the receiver thinks that node 20 updated its heartbeat count to 11. If in a world where clocks are perfectly synchronized, the timestamp can be a global timestamp in the sense that whenever a node increases its heartbeat, in all messages it can just attach its timestamp and it can send the message. Then all nodes will, since they uniformly agree on the time, they will be sure that look, at a certain timestamp, node number 20 incremented its heartbeat. But in a world where timestamps themselves are not synchronized, there is no clock synchrony, the timestamp itself is an approximate quantity. So, the timestamp for a given member will indicate at best an approximate estimate of when the heartbeat was updated. So, the way that we will set the timestamp is that whenever we receive a message about a member, we will, directly from the member, we will set the timestamp to that, right, the time of receiving a message, where clocks are not synchronized. So, how do we detect a failure? Well, detecting a failure again is an approximate activity. Say the heartbeat counter for a node hasn't increased in t fail seconds, then a node is presumed to have failed. So, let us assume that for whatever reason, either messages got delayed, or there was a partition in the network, or the receiver had crashed and then it recovered. There is a probability of a false positive, and this probability of false positive in this case is bounded by p fail, right, which basically, what is false positive? We think a node has failed, but actually it has not failed. Then what will happen is that we will incorrectly conclude that the node has failed. However, the entry in the message list is not removed, because a node can continue to get gossips about the failed node from other nodes, right? It can continue to get gossips. So even after it concludes it has failed, it will not remove the entry, it will rather keep it. So it thus waits for some more time and finally removes the node after t cleanup seconds, alright. So let the probability of the node still being alive be bounded by p cleanup, right? The probability that after t cleanup seconds the node is still alive, right? Another variant of the false positive. So both of these probabilities, p fail is equal to p cleanup, is equal to so when are both of these probabilities equal? Well, so we can see that after t fail seconds we conclude that look, a node has failed, but again there is a mistake probability, in the sense there is a probability of false positive of p fail. After that we wait for some more time, so this entire duration we can call it as t cleanup. So the question is that given the fact that we have come here, right, and in spite of that, if the node, we again wait for this much of time, in spite of waiting for this much of time, if the node is still not responsive, can we conclude it has failed? Well, maybe yes we can, and we can remove the list, and we can remove it from the list. But the probability of a false positive in this interval, right, which is again conditioned on the fact that we waited for t fail seconds and we didn't hear anything about the node. If we want this probability p cleanup to be equal to p fail, then it is obvious that this interval should also be equal to t fail. Hence, t cleanup will be equal to 2 times t fail. Alright. So that is when both of these probabilities will be equal. But as I said, there is no specific need of making them equal other than for some degree of mathematical elegance, right? So you can refer to the paper. But in general, having mathematical elegance while analyzing such complex systems is desirable. And to do that, all that we need to do is we need to set t cleanup is equal to 2 times t fail. Alright, let's do some more math. So let us assume that f out of n members have failed. So we need to detect all f. K out of n members are infective. So infective means that they are spreading the message about failed nodes. And the third point is only one node sends one message to another node in a round. So in a given round, only one node sends one message to another node in a round. So what is the probability of incrementing the number of infective nodes, right? So the probability of incrementing it, let us say that the current number of infective nodes is p inc k. The probability of infecting it is given by this expression. So let's work it out. So the first factor is the probability that one of the infective nodes actually sends a message, and this is k out of n because we are assuming a uniform probability of sending a message. Next, what is the probability of a node that is not failed and not infected getting the message? So the number of such desirable nodes for the sake of this probability calculation is n minus the number of failed nodes minus the number of infective nodes, n minus f minus k, and of course there are n minus 1 choices. So the total sample space is n minus 1, and thus the probability is this, and since they are independent events they get multiplied. So the probability of having k infected members in round I plus 1, let it be p ki plus 1. So p ki plus 1, if it is equal to k, we can infer the following recursive relationship. So here I would like to make a point that whenever a system is complicated and difficult to handle and we cannot come up with a closed form expression, we often try to set up some sort of a recurrence relation, right? And recurrence is related to recursion. where essentially is the same expression repeating over and over again. So, in such kind of a scenario where we have set up a recurrence, what we can say is that in the I plus 1th round, if we have k infected members, in a sense k members who have some information about the number of failed nodes. So, this is equal to either p inc k minus 1 times p ki is equal to k minus 1, which means in the ith round we had k minus 1 infected in infective members, and then there was an increment, and the increment is given by this expression. Or in the ith round we already had k infective members and there was no increment, which is given by this expression. So, both of them can be calculated, and we can use this recurrence relation to nicely calculate the probabilities that at the end of any round the number of infective members is equal to k. This can be done. So, the probability that there is some the probability that there is some process that does not get infected by, let us say, process P after r rounds, let it be mistake P comma r, right. So, we will use this expression, this probability P over here. So, P mistake P comma r is equal to 1 minus P kr is equal to n minus f. So, let us understand this slowly, alright. So, let us first break this expression down into its subcomponents and understand each of these components one after the other. So, the first thing says that look at the end of r rounds, what is the probability that n minus f nodes are infective. So, where does n minus f come from? N is the total number of nodes, f is the number of failed nodes. So, n minus f refers to all the nodes that have not failed. So, if all of those nodes at the end of the rth round are infective, this probability is given by P kr is equal to n minus f, alright. So, if at least one of the nodes, right, there is at least one, so some process means at least one process is still infective, is given by 1 minus P kr is equal to n minus f, alright. So, this is P mistake Pr, and so then this was for a given process P. If I want to look at all the processes, well then I can use this simple result of probability theory, where P mistake R is union of P mistake P comma R, which is kind of less than equal to, it is upper bounded by. So, P mistake P comma R is given by this expression over here, and it is upper bounded by the total number of non-failed nodes, which is n minus f times this quantity over here. So, which means that we have an upper bound for P mistake R, which is this expression. So, let us keep moving. So, let us discuss the performance results. So, the experiment that was performed in this paper is that the number of members, this number is increased from 1 to 200. So, what we see is that the failure detection time varies linearly in the log scale. So, it is, the probability is 10 to the power minus 9, increases from roughly 0 to 250 seconds, 10 to the power minus 6 from 0 to 210, and 10 to the power minus 3, 0 to 150. So, if one member has failed, so the bandwidth requirement is 250 bytes per second, and the time that is required is typically O n log n. So, if let us say we vary P mistake, right, the mistake probability, right, that we derived 2 slides ago, if we vary P mistake from 10 to the power minus 10 to 10 to the power minus 1 on a log scale, what we see is that for 150 members, the detection time reduces linearly, right, in the log scale from 200 seconds to 95 seconds. With 100 members, the detection time again reduces linearly from 130 to 160, and with 50 members, it again reduces linearly from 60 to 25 seconds. So this is the essentially a detection time versus the mistake probability. The mistake probability is something that we are willing to tolerate. Now let us discuss catastrophe recovery. So gossip algorithms, where essentially what we are doing over here is we are gossiping. They do not work in the case of network partitions. So a dedicated failure detector needs to broadcast messages and it needs to re-establish connections, right? So unless you re-establish connections, messages will not go to the part of the network that has been partitioned. So we can have a broadcast protocol where each second a node probabilistically decides to send a broadcast. This probability depends on the last time a node received a broadcast. So let's say if a node received a broadcast 20 seconds ago, then it broadcasts with a very high probability. And it can be a function, one of the functions of this form, t raised to the power a divided by 20, which fits well. Alright, so basically the idea is that if let's say a node has been receiving broadcasts from other nodes, it can reasonably be sure that the network is connected. But let's say a long time has elapsed and it has not gotten any broadcasts, then it tries to re-establish connections. So these were the, broadly speaking, the two papers that we discussed in this lecture. So the first was epidemic algorithms, right? So of course it's mentioned in the reverse order. And the second was a gossip style failure detection service.